I'm going to talk about complex adaptive systems, and I'm going to use ELSI as a case because we've established that most of the human systems are actually complex systems, and whatever we see, whatever we do, it's kind of emergence. So if you had too much wine and burping, that's not emergence, but the rest of it is kind of emergence. So it's hard to, I took so many notes for this presentation, and not seeing them is not easy. There are two parts. One is, in my presentation, one is my existential crisis, which started Tuesday. You know, most of us, I'm also confused with emergence and stuff. Something I realized myself a couple of months ago, the more I know about the topic, the more ignorant I get, because my current amount of knowledge prevents me learning new stuff about that topic. I have a, you know, that's like, that works, my knowledge works like a gatekeeper. And on this topic, I have a dissertation, so I know about these things, but as of Tuesday, I'm confused. I can't make sense of things, because complexity or emergence is quite different in human systems. But I like this challenge. I like being broken and confused, so I can learn new stuff. I can new angles on this topic. So I ask you to do the same during my presentation, please, because most of the concepts we are going to see in the next slide is understood differently in your current disciplines. When I say, for instance, catalyst, in chemistry, you know what catalyst is, but in economics, catalyst is something different. So you go to a pub, for instance, to, let's say, get laid, meet someone, and the pub owner sells you beer. That's actually catalyst in economics. Kind of makes that interaction faster, the pub owner. It's similar to chemistry, but different. So most of the concepts will be different. So I want you to keep an open mind during my presentation and be confused like I am already. So this is how we understand, I'm going to give you a narrative. This is how we understand complex adaptive systems and emergence in organizational and industrial psychology, organizational studies, or management, or business. So we have a large number of agents. It's us, or a company, or an organization. The more diverse, the better. Because if everybody is the same, you don't see much novelty. Remember, this is the business perspective, so we want to see novelty, something emerges, something innovative, something new. They're supposed to have interconnection, task interdependency, someone's output should be someone else's input, and things like that. That kind of communication, information exchange is important, because over time, these will accumulate, reach critical mass, and something will emerge. The process is mysterious for business folks, but that's okay. They only care about profit. They don't care about science. So process being mysterious is okay with them, as long as something nice emerges at the end. There are feedback loops, so think about the gossip stuff. I mean, you don't know what's going to happen if I tell you that, you know, I saw Jane last night and she was smooching the director, and you know, so you don't know it's unpredictable. It's that feedback loop, that gossip feedback will create something. And human systems, we see that kind of nonlinear communication stuff all the time. Far from equilibrium, edge of chaos is a sweet spot where order and chaos is nicely aligned. It's not too ordered, because if there's too much order, nothing emerges unplanned. And if it's chaotic, I mean, it's chaotic, we can't make sense of it anyway. So there's the sweet spot where you have some freedom, and also there's a structure in the overall system. Over time, influx of energy, money, ideology will accumulate, something will emerge utilizing that influx of energy. In human systems, adaptation is mostly considered as learning new stuff, but it doesn't have to be a formal learning setting. For instance, for the last 3-4 days, we are learning, for instance, how science is being conducted in Japan, how institutions function in Japan, or how a symposium is run here. Things like that. We learn from each other all the time. It increases our fitness. Or in my case, it decreases because I'm confused. I just want to go back and tear the pages of my dissertation that I wrote, some 7-8 years ago. Path dependencies is all the silly stuff we do. As you know, we don't get to see the big picture. We only have information from our immediate neighbor. Therefore, we do silly stuff all the time because we cannot know all information. And we don't have to. That's a good thing and a bad thing. And coevolution. So research networks have these things. We have these things. Let's think of ELSI. We have grad students, postdocs, senior researchers, visitors. All are different vectors with different agendas. Yet they work under ELSI to achieve a goal, to conduct Earth life science research. There is interdependence. Your lab mate's output is your input. You take it to somewhere else, then two others combine, write a proposal. So there is this connection, interaction between them. I'm assuming it is in that sweet spot. It's not a military institution, for instance. I mean, I don't know. I'm looking at the directors. They're smiling. That's not a nice smile. So maybe it is a little bit more ordered than I expected. But, as scientists, we have that freedom about our research. We can conduct research we want, the way we want. What's going to emerge? Papers, articles, collaborations, proposals, maybe new programs, new classes, maybe new institutes. We're going to close this one down, open a new one. I mean, their history is filled with such institutions. We're learning path dependency. For instance, that silly thing is how we publish. The way we publish is so bad. I mean, we are making Elsevier rich, right? That's path dependence. Nobody's thinking about that. Or, from my NASA research, I remember senior folks telling their students not to publish in astrobiology journal. You're an astrobiologist, getting money from astrobiology, telling students not to, because they can't get a job. You have to find a different journal, more reputable blog. This was 6-7 years ago, so things were a little bit... astrobiology, by the way, their index score is not bad. But that kind of path dependencies, we don't think about it, and we do, everybody else is doing. My senior is doing, I do the same. We're little minions in that sense. And that's normal, because university education is indoctrination. It's not the ideal. I mean, we have a philosopher of science among us. It's not the ideal stuff that science brings, good in humanity thing. So let's start. Let's start with the fun. So I'm using Web of Science. I'm going to talk about the things that emerge from ELSI, being a research network. So I did some bibliometric analysis of their publications, and I'm going to show the network and how you are actually producing science. But it has some limitations. Web of Science uses natural language paradigm, I should say. So for instance, John Harland, right? But you also have a middle name. Starts with W. So there are publications tagged in Harland J, Harland J W, Harland J space W. So these are the limitations. So I need to go back and merge all of them into one John W. Harland, for instance. So, and I'm going to show a couple of examples like that. Also, bibliometrics has its own limitation. Everything you do does not go into publication. This is just publication, not everything you do. So don't feel offended. Whenever I present bibliometric results, people, this publication is not included here. I did this, I did that, I created this summer school. Yeah, but this is only the bibliometrics part, okay? So keep that in mind. And also, This is only Web of Science database. There are two big databases, Scopus and Web of Science. But there's also Google Scholar, you know, that tags other stuff you do. You can see even your class notes on Google Scholar. There's spiders, roam around the web, bring that thing as your publication. But this is a little bit more selective. So maybe you publish something in a local journal. Maybe you published it in Japanese. It's not here. So again, not offended. But overall, ELSI has, in the last 6 years, close to 900 publications. As you can see, it's between close to 200, between 150 to 200 every year. That's not a bad number compared to other WPIs, but not the best number as well. Let's see. Okay, I can't start the video, Mike. Oh, okay, it starts, okay. So this is 2002. This is the Co-Authorship Network. So as you see, it is, just watch it for the moment. I'm going to show you this in detail anyway. So over years, the network is getting denser, growing. So it takes time. There is a delay in bibliometrics. When you start an institution, it doesn't happen overnight. It takes time to build up connections, create that trust relationship with collaborators. My main bread and butter is collaboration, so I focus on collaboration. So that was too fast. Don't say I'll go into the... Okay, no. So as you can see over the years how network is growing. The very first, this is Hirose-san's group. Actually, it starts with, you know what? Let's get into nitty-gritty stuff. So this is what we see in 2017. So this is what we are right now. The ELSI network, the publication network, in terms of co-authorship, starts with Yoshida-san and Irofune-san in 2012. Then we see Hirose-san's network, merging these two networks. And on the third year, we see these other clusters. So currently there are 14 clusters. Every color is a cluster. The nodes, the size of the circle is an indicator of how many publications that person co-authored. And the lines show that how many publications they co-authored together. So it's a basic network now. So you see these clusters, how it grows over time. For instance, this group is, you know, kind of lonely souls. I don't know how to interpret these results because I'm not an earth science scholar, but we can see these nodes and this nodes, Fujimoto-san's nodes, are a little bit separated than the rest of it. And that's normal. I mean, this is not Lego. At the end, all pieces doesn't have to fit together. But sometimes funding agencies expect that. Well, it doesn't have to be like that. As you can see, the closer they are, it means their researchers is closer to each other. So this helps us to, let's zoom in one area, for instance, and see more details. So who is connected to who and how through publications? Of course, this is the most, these are the 500 publications, 500 links, top 500 links, not everything, otherwise it will be really messy. But we can easily see. This is good in terms of collaboration. If you identify what I call the bridging people and invest in their bridging activities, your network will be healthier. I'm going to give a silly example. Experience coming to Japan, Tokyo. This is really fun. Okay, it's getting spooky. Okay. But some people may not enjoy Japan. But if you know Mike or Tony, your experience in Tokyo would be really grateful. It will be fun. They'll take you out, show you places, show you food places, and things like that. So they're doing a good job in terms of attracting people to here. In the same sense, some people can talk more than one disciplinary language and be a connector between, say, geological sciences and life sciences. So if you invest in these people or clear the path for them, your network will be healthier. I'm going to show some numbers on that. For ELSI, the proportion of life science-related publications are a little bit lower than geo or planetary science-related publications. So using my time wisely, and I know that I'm standing between you and your lunch, I'm moving on. But we can discuss these later. Okay, let's get back to the slideshow. So also another important aspect for WPIs and ELSI is having globally visible, globally recognized science, and that happens through collaboration with folks elsewhere. So these are the top 25 countries that ELSI folks collaborate over the last 6 years. And as you can see, it starts with a very simple network, Japan and the other countries you don't see, but one of them is France, Germany, and USA. See the network, how it grows over the years. At the end, it will be for 51 countries all over the place. Normally, USA is always on top. It's a research behemoth in that sense. Not surprising. But for ELSI, England, France, Germany, China, they are important nodes. I'm so sorry that this doesn't fare well. I mean, let's see. Luckily, I brought everything with me. So now you can see better, maybe. And some of them, I guess, probably the EON postdocs coming and going, or the workshops that are being held at ELSI throughout the year. So they really produce some very strong collaborations. Compared to other WPIs, ELSI in that sense is really good, establishing international collaborations and stuff. Of course, it's not only the country we can see, we can also see the institutions, and specific institutions, I mean. So, as you see, most of them are institutes in Japan, and that's normal. Proximity is important in collaboration and these emergent structures, because there is a cost, as you know, there's a cost to get an airplane ticket. But it starts with Tokyo Institute of Technology in the middle. At first, there are only 8 institutions ELSI collaborated, or Tokyo Institute of Technology collaborated. But over time, it gets dense. Caltech, CNRS, NASA, University of Arizona, highly reputable institutions are part of this network through ELSI. And I guess this is the last of it. Let me switch to the more detailed version for a second. Not surprising that But ELSI is also, it's a hub for scientists in Japan as well, not only international. And this is another emergent structure that we see through the work conducted here. Come on. Okay. Moving on. And as I said earlier, I study interdisciplinary science. So these are the areas, top 25 areas ELSI researchers publish. As you can see, geosciences, planetary sciences, quite a lot compared to life sciences like biology and biochemistry or microbiology. But that's also expected because different disciplines have different publishing habits, publishing frequencies. A good chemist throughout his or her career publishes maybe 250, 300 articles. On the other hand, a biologist publishes maybe 50 to 60. So that may explain the differences here. Some work take more time. Simulation, for instance, it's easier and faster to publish that kind of modeling work and stuff. So this could be an indicator of that. And again, we can see how that network developed. This is a keyword map. So the software I use tracks the titles and abstracts of the articles and the keywords of the articles you submitted and creates this co-occurrence map. This is good because in previous boxes, the disciplines are a couple of researchers' framework that work at Thomson Reuters. But this is keyword, this is bottom-up. This is bottom-up formation. Let me show you this in detail because I believe this is important. You are going to make more sense of it than me. You can see different clusters, let's say. So, what is this, John? It is, okay, it's pressure. Okay, so no discipline is attached to it. But if you're interested in one of these keywords, and if another researcher is interested in these keywords, you may not know each other. It is, again, pretty common not to know who's doing what, especially in these kind of interdisciplinary settings. And we can overlay these maps, co-authorship map with the keyword map, and see hidden potential collaboration opportunities and things like that. Or I think high pressure was not good. Let's see. So what is this? Oceans? Geochemistry. Okay. See, now we have, and see, I guess this is more life science because I see. Yep. More life sciences, microbiology, and things like that. So these networks didn't happen. These networks did not exist before 2012. See, this is what we say emergence in science and technology policy studies, for instance. So I'm going to move fast and finish stuff. I don't know if I'm receiving any questions. Oh, we can also see the funding thing. And I'm going to show you the error here. So through your papers, we can also see if you got additional funding, because you acknowledge them. But as you can see, this is this one, this one, this one, probably this one too, this one. They're all the same. But it's like Herland J, W, Herland John, W. They're entered separately, so this doesn't work. I have to go back and re-edit that data. That's why it takes a lot of time, because I have to go into every field in the metadata, find these discrepancies and fix one by one. These are the journals you prefer to publish. See, now we are moving into the co-evolution part of complex adaptive systems. These emergent systems, we were talking about yesterday, I think it was you, Sean, or maybe it was Olaf. What we consider emergent is a new structure that results in, or that has the potential to create new interactions. So you publishing in these different journals is actually an impact on the greater science of things and potential to create new networks and new interaction opportunities. These are the mediums. It's also good for the funding agency or the managerial aspect. You can see, are they high impact journals or not? And actually these are some of the really highest impact journals that are available.
Arsev, we have a question coming in.
Okay.
Would you like to field it? So Nicholas asked, can we get at causality in this data to escape Goodhart's law? When a measure becomes a target, it ceases to be a good measure. Problems?
That is an excellent question. In my experience with NASA, for instance, I was doing this similar work with NAI teams. The first 2 years were pretty good because annual report data was available for me to utilize. But once the PIs realized that that's the data set I'm using, that annual report data becomes so different, mutated so in a different way. So I don't know. The more common these practices become, the more Goodhart's law will be in practice. But there are some predictive works. For instance, if you are involved in a prize network, it means that you're going to get more prizes during your scientific career. So early on, getting a prize on something, will increase your chances of getting funded in later years. There are some predictive studies looking at people's postdoc papers and try to see if they're going to be good researchers when they're tenured or not, but not accepted by everyone. They are a little bit trivial. So I think there is some room there for improvement. And especially now, machine learning algorithms are used to predict these stuff, they're looking at 20 million publications at once and track, doing a temporal analysis, track stuff, but we are not there yet. And it would be, you could easily find a job at NSF or someplace if you can develop that algorithm. Citations is another impact. It's again coevolution. As you know, in complex adaptive systems, when something emerges, every agent in the system has to reposition themselves. So when you publish something, find something new, people have to cite you. And they have to change their findings, interpretation accordingly. And we know that 80% of all citations are in favor of the published work. Only 20% criticizes, in general, of course. If you're talking about the arsenic-based life paper, that is a different story. But 80-20 rule works in citations. This is a long one, sorry. So which people, which country, who cites you? Not only Japanese folks. Again, this is an indicator of your international reach. Folks in these places cite you. And I only put these two for the sake of time. And also you have an interdisciplinary impact, because these fields, researchers from these fields, or journals, I should say, in these fields cite your research. I'm going to give you a moment so that you can take it in. I would like to thank to Kaoru and Seda for helping me with the data. These are some of the articles I used, and some of them are actually mine. But this is how we approach in organizational studies. This is how we approach to complex adaptive systems and emergence. Through the narrative I described a large number of diverse agents interacting, getting something additional to the system that will result in organizing or creating a new structure, emerging a new structure and stuff. In our research networks case, I focused on the publications and collaboration and the network stuff, but there could be more. Of course, for more stuff, it's not easy to collect data, because I cannot put, for instance, RFID chips on you, tracking you all day, and see who you are talking to, what kind of insights you're gaining from that other person, and things like that. But we know that from experience, these things happen. That's why it's important where the water cooler, water fountain is, because people really talk while drinking water or getting coffee or going to the restroom. Therefore, we don't say corridor anymore, for instance, in design. We say information pathways, because you can put a lot of posters and information on a corridor wall and get people exposed to some different types of knowledge and things like that. But again, it's not easy to collect that data, and I didn't want to bore you with lots of qualitative stuff in this presentation. So I'm done on time. If you have any questions, discussions, my understanding of emergence could be, not could be. I'm convinced that it's different than you in the last 3-4 days, but that's how we see the world for the moment.
Thank you. That's like Arsev. So Eric, we can start with, with you. Let me get you the box, just a second.
I want to throw.
Oh, you want? Okay, go for it. Oh, good job.
Thanks, Arsev. I want to ask you about the future regarding methods. So, hard to gather the data, but that's now a thing that we know how to do. You then have charts, networks, and so forth, and the first thing that you can do is organize and aid in visualizing the data. Another thing that sometimes one can do involves analytics for things that are not evident from the visualization tools. So if I'm Google, I put together a relatively simple network representation, but then I use a very compute-intensive algorithm to understand properties and, in fact, create a semantics of that network that's not evident from looking at the local features. If I'm an analyzer of systemic risks for banking systems, I'm not so compute intensive and I'm not as diverse in what I can do, but I can still use network properties to understand which banks are focal points for systemic risk, and I can feed that back on regulatory policy and reserve requirements and stuff like that. It looks like in much of the bibliometrics literature, we've made huge strides in giving people the ability to see data. What is the most important thing that they're not good at seeing where formal tools are helpful and interesting to develop from here?
That is an excellent question. I think that ties it back to the limitations of bibliometrics, in my own opinion, because bibliometrics is the end result. So traditionally, we assess scientific networks based on two things, whether they publish or whether they are within the limitations of the budget we provided. As long as they do these two things, we're good. And funding agencies don't think something else. They are content with these two criteria. Confusing. However, we know from experience that most of our ideas, studies don't end up with a publication all the time. And over time, we accumulate lots of knowledge, experience, wisdom that is really hard to track, almost impossible to track, but will result in something. So what you did, what you've been doing for the last 20 years may result in something really extraordinary in the next 2 years, and that will be attached to ELSI, but not to your career that had been happening for 20 years. So tracking that would be really interesting, but for that, I need to convince you and a couple of you to a lab discuss things in detail, maybe throw at you some problems, record your discussions and stuff, and then use really heavy computer support to analyze how you think, come up with novel ideas and things like that. And actually this is being done, but only on a very limited scale. I know, for instance, some work's been done by Steve Fiore in Florida. For instance, they had a shuttle problem, NASA, and they fixed it some years ago, maybe 5-10 years ago, with a toothbrush. And that they analyzed the discussions between the engineers on the ground and astronauts up there. It's all recorded. They coded all the discussions. And then using these codes, they come up with a scheme how this novelty occurred and things like that. But it brings lots of privacy issues because your ideas are valuable and someone can easily grab them and things like that.
Yeah.
I don't know if I answered your question.
Yeah. So it's a hook to semantic network methods and things
Yes.
like that if one were to choose to develop such things.
Yes.
Yeah.
That's a better technical explanation. I see hands here.
Hi, Arsev. You spoke two kind of sub-questions. You spoke briefly about funding kind of intermediate hub, either personnel or ideas to help bridge a network and presumably make it more robust. You talked about the advantages. Are there any kind of structural weaknesses to that kind of approach? And can this approach be amenable to addressing other systemic desirable traits or kind of canaries, to use the phrase that Dr. Penn was speaking of? Other things that might be desirable to change in the future, such as research funding, efficiency, productivity, gender disparity in citations, these kinds of open-ended questions.
Traditionally, these systems are supposed to be bottom-up. The formation should be bottom-up. But of course, this is business stuff. Nobody wants to give power to someone else. So there is this also, in the case of research funding, governments don't want to give that power. So they want to control the system through either money or some other power dynamic. So in these cases, it's a mix of bottom-up formation, but also top-down management. Because, for instance, in the American case, NSF goes out and says that I'm going to fund projects in this field only. So normally, that's called strange attractor in complex adaptive systems. It's supposed to be natural, but in this case, it is enforced by someone else to the system. There is actually ups and downs in it. Sometimes we scientists are highly narrow-minded. You know, we get like that. I mean, university education is kind of indoctrination. We are trained to see certain problems, approach them from certain angles, and only certain things are important for us. But there's a huge life outside. There's other disciplines, and sometimes we get this tunnel vision. So it is good, in my opinion, to have that kind of top-down approach. But if they are in the wheel by themselves only, for some political reasons, ideological reasons, they can steer where free science should go. And it's give and take. I don't have a clear answer for that, but I like this messiness, to be honest. Because where is messiness, where is diversity, I believe the system has a better chance of fixing the errors and come back to a dynamic equilibrium point. That makes sense.
Okay, sorry. In the interest of time, we're going to have to call it here so we can accomplish the goal of people being able to gather and get to lunch in time to beat the rush. And I think we should thank Arsev and Alex again, and thank yourselves for being here for the session this morning. Good job, everyone.